Hello everybody, welcome to Pre-Calculus, Unit 1, Day 1, first day of notes. This is going to be a little bit of review from Algebra 2, but we're going to get right into it here. We're going to start with functions, a few definitions. A relation. A relation is simply a mapping of inputs to outputs. Could be car model to color, could be student name to height. The domain is the set of all inputs. We're probably more familiar with coordinate plane, so we're going to talk about the x values. That's known as the domain of a relation. And the range, as you can probably guess, is going to be the set of outputs, or if you're talking on the coordinate plane again, it's going to be the y values. So our first example here, I give you this relation, and I just want you to list the domain. All right, well, that's pretty straightforward. The domain, we're going to use x is an element of. So you want to specify it's the x variable, and that symbol's element. And you're just going to list all the x coordinates. 2, 4, 8, and 12. And our range will be all the y values. And we're going to say y is an element, and then list all the y values. So 4, 18, you do not have to list it twice, and 32. Okay, so first thing, identifying domain and range of a relation. So now a specific type of relation is called a function. And a function is a relation in which each element of the domain is mapped to one and only one element of the range. And that's a very important concept. It's kind of a simple concept, but it's easy to get that backwards. So first thing we're going to do here is list some functions and some non-functions. We're going to use different notations, a set notation, mapping notation, and then our typical f of x notation. So here's an example of a relation that is a function in set notation. So I'm going to have my parentheses indicating an ordered pair. So I've got 2, 3, 3, 4, 5, 6. And just a quick review of why that is a function, because each element of the domain is mapped to one and only one element of the range. So 2 is only mapped to 3, 3 is only mapped to 4, and 5 is only mapped to 6. All right, well, here's set notation of a relation that's not a function. 1, 2, 1, 3, 2, 4. So why isn't this a function? This is not a function because you can see the 1 is mapped to 2 in the first point, and then the second one, it's also mapped to 3. So that element of the domain does not have a unique element of the range. All right, so another type of notation for the same thing is what we call mapping notation. So I'm talking about a completely different relation here. We use kind of ovals to represent the domain and the range, and I'm just going to make some stuff up here. I'm going to draw arrows to indicate what is mapped to what. I'm going to say 1 is mapped to 4, 2 is mapped to 4, and 3 is mapped to 5. So this looks a little strange. It looks a little bit different than the type of function up above, but it still is a function because 1 is mapped to 4, 2 is mapped to 4, it doesn't go to a separate one, and then 3 is mapped to 5. So let me illustrate this mapping notation with something that is not a function. All right, it's going to look similar, but hopefully you guys will see. So the reason this one is not a function is because 1, that's an element of the domain, is mapped to 2 different elements of the range. So that's not going to be a function. And our f of x notation, simply, I'm going to create something here. F of x equals, let's just say 3x plus 1. All right, that is a linear function. And here's another one, f of x equals plus or minus square root x. Now, don't worry if you don't know what this looks like right now, first day. But I'll just do a quick sketch here. 3x plus 1 is going to look something like this. And plus or minus square root x is going to look something like this, sideways parabola, kind of. All right, we're going to discuss next why plus or minus square root of x is not a function, while 3x plus 1 is. All right, that's our definition of vertical line test. So all functions pass a vertical line test. Well, what is that? Well, if I have a function like that one we just talked about, 3x plus 1, you can draw a vertical line anywhere on that graph and it will only intersect at one point. So that would be a function. A non-function, like that plus or minus square root x, sideways parabola, a vertical line would intersect in two places. It only has to intersect in two places in one spot. So for example, if you can draw a vertical line that only hits once, that's okay. But if any vertical line hits that graph in 2 points, it's not a function. So we have what are called parent functions here. And we're going to talk about these with some key points. These are functions that you need to be able to graph without the use of a calculator and without coming up with an XY chart. You have to know the relationship. The first one is a linear y equals x. And that's a simple graph. Looks like this. You can name any key points you want on here. I'll start. We got 0, 0. We got 1, 1. We got 2, 2. Pretty easy relationship. The y value and x value are the same. Obviously, you can go into the negatives as well. The next one is an absolute value. Y equals absolute value of x. Another graph you should be very familiar with. So basically what happens here is this part of the graph looks very similar to the linear. And obviously hits the origin here as well. But the absolute value is the distance from 0. So basically, since it's a distance, it's always positive. So what we're going to do is we're going to take all our negative y values and make them positive. So it looks like this. So there are 3 key points on our absolute value graph. Okay, another one, quadratic, our parabola, y equals x squared. There's our basic shape. So think of this as you're squaring the domain. So we'll start here with 0, 0. And then I go over 1. So my domain is 1. Well, if you square 1, you get 1. Okay, well, let's say I go over 2. Well, if you square 2, you get 4. So it should be pretty easy to come up with those key points. The next one would be 3, 9. 4, 16, 5, 25, so on and so forth. So it's a very easy relationship. You're squaring. Okay, let's talk about our square root. A little bit more challenging here. I know you have experience with this, but let's think about it for a second. Square root. I cannot take the square root of a negative number. You can't take the square root of a negative 1, right? It's an imaginary number. And we're talking about real numbers here on the coordinate plane. So 0, I could take the square root of. So it's going to start at 0, and the graph's going to kind of look like this. So think about it. If I put in 1 for my domain, the square root of 1 is just 1. Well, you could put in 2, but the square root of 2 is not an integer, so it'd be kind of a mess to graph. So I'm going to think about what type of numbers can I take the square roots of, and those are perfect squares. So the next number that's easy for me to take the square root of is 4. So if I go over 4, and then you take the square root of 4, you're going to get 2. So 4, 2 would be the next convenient key point. And then again, think of the other numbers you'd want to take the square roots of. 9, so 9, 3, 16, 16, 4, 25, 25, and 5, so on and so forth. Okay, our next one is a cubic, and we're cubing our domain. So 0, 0, as you'll notice, is on most of these graphs. And then it's going to kind of look like this. Put in a 1. 1 cubed is 1. Put in a 2. You cube that, you get 8. So now what's interesting here is what happens when you cube a negative number. So as you're looking at this, it looks pretty similar to the right side of our quadratic. Obviously, it gets a little bit steeper. But what happens when I put in negative numbers? Well, if you remember, when you cube a negative, you get a negative. So it's going to actually look like this. And that's going to be negative 1, negative 1. This is going to be negative 2, negative 8. And so on and so forth. Negative 3, negative 27. And we only need 3, but you get an idea of what it's going to do in that direction. So now we've got the cube root of x. All right, so that would be the cube root. And as you can probably imagine, it's going to be similar to our square root, except now I'm taking the cube root of numbers. So again, 0, 0, you know, is on most of these. 1 is easy to work with. The cube root of 1 is 1. But now let's think about what number I want to take a cube root of. 2, nope, messy. 3, 4, 5, 6, 7. It's not until we get all the way over to 8. So at 8, I can take the cube root of 8, and that's going to be 2. So again, it looks similar to the square root. It's a little flatter. But think about what happens with the negatives. If you take the cube root of a negative, you get a negative. You can take the cube root of negative numbers. So here, I get -1, -1. And then the next convenient one for me is going to be -8, -2. All right, we've got 3 more. The next one you probably remember from Algebra 2. This is our exponential. Y equals a to the x, and it just kind of, depends on what our base of a is. For our graph, we kind of have a pattern here. One point that's on all exponentials, all right, unless we do some sort of shift or dilation, is going to be 0, 1. Well, why is that? Because our exponent is the x. If you put a 0 in for that exponent, anything to the 0 power is 1. So 0, 1 will be on all these exponentials. And it turns out I'm going to get something that kind of looks like this, if you remember from A2. Now again, it kind of depends on what that base is, but if you think about this, if I go over 1 in the x direction, that means my exponent is 1. Well, anything to the first power is just itself. So 1 comma base, or in this case 1a, is going to be on this graph. And if I put in a -1 for the x, you remember your properties of negative exponents. Negative exponents take the reciprocal of the base. So at -1, the y value is going to be 1 over a. So those are some key points you really need to know, especially this -1 comma 1 over a and 1 comma a. And there's another thing here I want you all to note. So we got something special here. For the first time we're seeing it. It's called a horizontal asymptote. So we have a horizontal asymptote at, that's going to be y equals 0. Again, unless there's some sort of vertical shift, that's always going to be an asymptote. So your exponential will not cross that. Okay, next, everybody's favorite, our log graph. Y equals log base a of x. All right, so one thing we're going to get into a little bit more today are inverses. These two graphs are inverses, our exponential and our log graph. So if you remember, one of the things that we can do is we can just switch our x and our y. So this point right here, 0, 1 is going to become 1, 0. Instead of 1 comma a, we're going to have a comma 1, base 1. And this one right here, instead of -1, 1 over a, this is going to be 1 over a comma -1. So those are going to be the 3 key points on our log graph. And one thing to note here, in this case, we're going to have a vertical asymptote at x equals 0. So again, the x and the y are just going to switch. Okay, very quickly, our last one, we called this our inverse graph. It's kind of interesting. Y equals 1 over x. And for this one, I'm only going to do 2 key points. So if you think about it here, what happens if I put in a 0 for x? 1 over 0, that's undefined. So that's going to be an asymptote. If I put in a 1, I get a 1. So this point right here is going to be on there. It's 1 comma 1. If I put in a 2, I get a 1/2. If I put in a 1/2, I get a 2. It's an inverse graph. Looks like this. Now what happens if you put in a -1? You put in a -1, you get -1. Put in a -2, you get -1/2. So this graph's going to have 2 pieces, and it's going to look like that. And in addition to our vertical asymptote, we also have horizontal asymptotes. So we have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Hey everybody, welcome back. This is still Unit 1, Day 1 notes. We're going to pick it up here with our transformation rules. Again, hopefully it's a little bit of a review from A2. So first thing we're going to look at here is a constant added to the outside of your function. All right, what this is going to do is this is going to be a vertical shift. All right, and in particular, what it's going to do is that number is positive, it's going to shift your graph up. If that number is negative, it's going to move it down. What if the constant is added inside the function? So in this case, we're talking about an absolute value. It's inside the absolute value bars. Well, in this case, it's going to be, we call a horizontal shift. All right, now this is a little bit weird, but if it's positive, it's going to move it to the left. So if it's x plus 2, that means left 2. Negative is going to move it to the right. Okay, next, multiplying by a coefficient. This is what we call a vertical stretch. And it's not really a true dilation, because a dilation stretches or compresses in both directions. You could say a vertical dilation, but we prefer to call it a vertical stretch. And if that value of a is between 0 and 1, it's going to make the graph shorter or give it the appearance of getting wider. And if a is greater than 1, it's going to stretch it upwards and make it taller, or again, give the appearance of it being narrower. All right, so next, what if we have a negative included here? So the first one is multiplying by a negative outside. So if the very first thing you see is a negative, what that's going to do is reflect it in the x-axis. Now this is also a little bit tricky for our purposes here. I want to say reflects on the horizontal. Because you can say a reflection in the x-axis, but that would have to be done first prior to any sort of vertical shift. So if you say a reflection on the horizontal, you can shift it up, but then there's that imaginary horizontal line that you would reflect over at that point. So the next thing you can probably figure out as well, multiplying by negative on the inside. So the negative is inside the function, inside the square root, inside the absolute value, inside the squared, whatever it happens to be. So that's going to be a reflection in the y-axis, or again, probably better off to say a reflection in the vertical. Okay, because you can say reflection in the y-axis if you do that first before any type of horizontal shift. All right, so now what we want to do is we want to combine those 9 parent functions we talked about in the first part of the lesson with those transformations, because your goal here is to sketch these without using a calculator, without creating an XY chart, while including key points. So here's how we're going to do it. Okay. So first of all, I need to recognize that that's an absolute value. So I know, oh, absolute value, it's going to kind of look like this. I'm going to make a little thumbnail sketch. Next, I have to identify, all right, well, what's going on here in this graph? I have a -3 that's inside the function. So that's a horizontal shift, and that's going to be right 3. So what I have to do now is I have to take this V and shift it right 3 and make a sketch for that. Again, you don't necessarily have to write all of this down. I would like you to write down the transformations taking place. But now I go to make my sketch. 1, 2, 3. There's my V. Now how do I get my key points? Well, the easiest one is probably get that vertex right there. That's going to be 3, 0. Next, where do we go to get the next one? Well, I have to go right 1, up 1. So that's going to be 4, 1. Then from the vertex, I go right 2, up 2. So that's going to be 5, 2. So I got those key points without coming up with an XY chart and just using the transformations and my knowledge of the parent function. Okay, go to number 2. X squared. So again, it's a quadratic. I'm thinking, oh, quadratic's going to look like this. I've got 2 things going on here. Number 1, this is outside the function. So this is going to be a vertical shift. It's going to go up 1. This right here is a vertical stretch times 2. So what it's going to do is it's going to take all of our key points and stretch them up 2. Now 0 times 2 is still 0, so that vertex is not going to move. So let's see here. The first thing I need to do is go up 1, so that vertex is going to be here. Now this is all about a pattern. When you get to this point, it's about a pattern. And I know it's kind of hard to do this virtually, but what I'm going to do is understand in a parabola, I go out 1, up 1, out 1, up 1. Because if your domain goes out 1 and you square it, you go up 1. Now this is going to be a little bit tricky because we also have that vertical stretch of 2. So instead of going out 1, up 1, you have to multiply that y by 2. So I'm going to go out 1, up 2. So I have to double that distance. So these two key points here and here, okay, represent, that's going to be 1, 3. This is going to be negative 1, 3. And that point right there is going to be 0, 1. So for quadratic, that pattern from the vertex is out 1, up 1, out 2, up 4, out 3, up 9. Right, because that's our squaring pattern. But that vertical stretch is going to multiply all of those y values by 2. So out 1, up 2, out 2, up 8, so on and so forth. Okay, let's take a look at number 3. We've got a cubic. All right, so we need to recognize our parent function. I also need to recognize what that's going to look like. So I like to do these little thumbnails. Again, you don't have to, but it's going to look like this. See, I recognize that pattern. And what am I doing? A negative 1 inside the function is right 1. And a plus 2 here is going to be up 2. So, make my sketch. I'm going to go right 1, up 2. This point right here that I just plotted on this graph, this coordinate 1, 2, represents that point right there. So now I need to know my pattern. Out 1, up 1. Out, I guess I'll use a different color here. It's kind of hard to do. Out 2, up 8, because I'm cubing. Okay, so from here, out 1, up 1. I don't really have room here. I apologize to go up much further, but I know this coordinate's going to be 2, 3. Going towards the left, I go left 1, down 1. So that's going to be 0, 1. And then I'd go left 2, down 8. So 1, 2, 3, 4, 5, 6, 7, 8. Be about right there. Again, we're just making sketches. Now, because this one is probably the first one we've done here, it might be a little bit confusing. One thing that you can do is check your coordinates. You can put your x's back into the original. I only want you to do this after you get your sketch, not to come up with the points. So what I'm going to do is I'm going to take this value, let's start with this one, this value of x, 2, I'm going to plug it in right here. I'm going to do some mental math and see if I end up with a 3. So let's put a 2 in for the x. 2 minus 1 is 1. 1 cubed is 1. 1 plus 2 is 3, and that's what I got right here. You can do the same thing with a 1, you can do the same thing with a 0, and you should get your y coordinates. Okay, so that's a way you can check it at the end, but I want you doing this process without the xy chart. Okay, example 4, we've got another quadratic here, so I'm actually going to come back to this. I don't want this video to run on too long, so let's do some different ones. Let's go to 5. I've got a square root graph here. I'm expecting something like this. Now, what I have going on is a negative in front, which is a reflection in the horizontal, or you might say your x. And I got a plus 1 that's inside the function. It's underneath the square root, so that's going to be left 1. All right, so left 1. This point right here represents that point. I shifted it left 1. Now, I have to incorporate my reflection on the horizontal. So that means over the x, because I didn't go up or down at all. So now the shape of this graph is going to look like this. And again, we have to recognize the pattern. From here, I go up 1 over 1. And then I go or over 1, up 1, I guess you should say. And then you go over 4, up 2. So I go right 1, down 1. That coordinate right there is going to be 0, negative 1. And then I go over 4, 1, 2, 3, 4, down 2. That coordinate is going to be 3, negative 2. And then this coordinate right here is negative 1, 0. And again, let me just check one of these just to make sure I'm on the right track. I'm going to check this x. I'm going to plug it into the original equation there. And what should happen is I should end up with a negative 2 coming out of that equation. So let's plug in a 3. 3 plus 1 is 4. Square root of 4 is 2. Then you negate it, so that's negative 2. That checks. All right, so I'm pretty confident that that graph is correct. Okay, 6 is a little bit silly. You'll see why here in a second. But one thing that's very important, when you notice you've got something minus x, you must factor out a negative first. So I'm going to put a little asterisk by this one. And say factor out the negative. All right, so I'm going to rewrite this so it looks like this. Y equals 4, absolute value, negative, parentheses, x minus 2, close your parentheses, close your absolute value. The reason for that, if you don't factor out that negative, your horizontal shift is going to be wrong. Because when you look at the original one, you might think, oh, I'm going to go left 2 because it's a positive 2. But it's not. It's actually right 2. Okay, so you can see that right here. So that's going to give me a vertical stretch times 4. This is a reflection. It's inside the function. So it's a reflection in the vertical, or you can say the y, and that's why I said it's kind of silly because it's absolute value. If you reflect the absolute value, it's not going to change. A v reflected vertically is still a v. And this right here is going to be right 2. All right, let's make a sketch of this. Absolute value is a v. This is right 2. That's going to be my vertex. All right, so that's 2, 0. The reflection is vertical, so it's not going to change it really. And I've got a vertical stretch of 4. So normally with our absolute value, we go out 1, up 1, out 2, up 2. But since our vertical stretch is 4, we're going to go out 1, up 4. So it's going to be a very narrow or steep v. So my key points, I've got 2, 0. I've got 1, 4. And I've got 3, 4. And again, one thing you can do here very quickly, let me just take this one, plug in a 3 into the original. It's already highlighted yellow, but let's plug it in right there. I put in a 3 there, I get 2 minus 3, that's a negative 1. But I take the absolute value of that negative 1, which makes a positive 1, and then I multiply that by 4, so I get a 4, and that checks with what I have right there. So that point is on there. You can check the other two just to make sure. Hello everybody, welcome back. We are still on Unit 1, Day 1. This is the third part. This will go a little bit quicker. We're going to do 2 graphs real quick here, 7 and 8, and we're going to write some equations. So number 7, we've got an exponential function. All right, so if you remember, your thumbnail of an exponential function kind of looks like this. We have an asymptote on the x-axis. But what's going on? I've got a negative out in front, which means I have a reflection in the x, or the horizontal. This 2 is a vertical stretch times 2. And my base is 3. All right, so let's see here. It's going to be kind of a challenging graph without the use of a calculator, without coming up with the next y chart. Okay? Let me just scroll down here a little bit. Okay, so base is 3. I've got a vertical stretch of 2. So the first thing I want to do, and also I'm reflecting in the x. So my graph, because of this, is going to look something like that. So if you remember, your key point of all exponentials is 0, 1. Well, I'm reflecting that in the x, so it's going to become 0, negative 1. But then we've got a vertical stretch times 2, so it's actually going to be 0, negative 2. So my graph's going to go through this point right here. I don't have a vertical shift, so this is still an asymptote. But what's going to happen is my graph's going to look like that. And again, I'm just making a sketch. I just know that's going to be the general shape. I know this point right here of 0, -2 is going to be on it. So what happens? Well, my next key point, if you remember, up here was 1 base. Well, I have to do two things. I have to reflect that in the x, and then I have to multiply that y coordinate by 2 because that's my vertical stretch. So my base is 3. So normally my key points for a function, exponential function with a base of 3 is going to be 0, 1, and 1 base, 1, 3. All right, well, I have to take that 1, 3, reflect it in the x, so it's going to be 1, -3, and then multiply it by 2. So my graph's not super accurate here, but I'm just going to label this as 1, -6. All right, so same thing. If I go in the negative direction, it's -1, 1 over base. All right, well, -1, 1 over base, I have to reflect that in the x, so it's going to negate it, and then you have to multiply that by 2. So this is going to be -1, -2/3. And those are 3 key points on this function. Again, this is a little bit challenging, so let's just check. Let's just take one to make sure we did it correctly. I should be able to plug in a 1 into this function right up there for the x, and I should get a -6. Well, let's see what happens. You plug in a 1. 3 to the first is 3. 3 times 2 is 6. Well, 3 times -2 is a -6, or you can negate the 6 at the end. Doesn't matter. But anyway, I get a -6. All right, so I'm pretty confident I did that correctly. You can plug in a 0. Anything to the 0 is 1. -2 times 1 is -2. So these two both work. -2/3 is a little bit more work in terms of that exponent, but you can use your calculator if you want just to verify it. So I'm pretty confident that this is correct. Okay, let's look at our last one here, a log graph. So a log graph kind of looks like this, where I have a vertical asymptote. If you remember, key points here are going to be 1, 0, and base 1. But then what we have to do is we have to use these transformations. Well, this one's going to be kind of easy because, look, I have a +4 inside the function. That's simply going to be left 4. All right, so our sketch here, left 4. And that's going to be where my vertical asymptote goes. So if you think of the pattern, again, it's about a pattern. It's 1, 0. So if I had to shift that point left 4, so that would be this point here. My base is 4, or sorry, my base is 10. That's the other thing I forgot to mention. If you don't see a number down there, if you remember, it's called a common log. And that simply means the base equals 10. So I'm going to go over 10 up 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up 1. And I'm sketching this in here. So this key point over here is -3, 0. And what's that? 1, 2, 3, 4, 5, 6, 1. And there's a couple things you can do. The next one's going to be base squared 2. Well, 10 squared is 100. You can't plot it, but you can write the coordinates down if you wanted to. You usually have to subtract 4. So that's going to be 96, 2. Or you can remember the pattern, this point right here. Basically what we do is we have to go left 1 over the base, so it'd be 1/10, and then down -1. So this one right here is going to be 1, 2, 3, -3 and 1/10, comma, -1. And that'll be our third key point. Again, if you remember from logs, let's check 6, 1. Plug in the 6. 6 plus 4 is 10. What is log base 10 of 10? Well, remember, if those two are the same, that's just equivalent to a 1. And that was our y coordinate there. So I know that works. You can try the others, but those will be the same. They'll work as well. Okay. All right, so the last thing we're going to do, and this is going to go a little bit quicker, is we're going to write equations of functions based off of verbal description. So they're going to give us a type of function, linear, quadratic, cube root, and they're going to give us various transformations. We just have to write the equation. All right, not a whole lot of work to show here. I'll try and do a little bit. So the first one here is a linear equation. So that's going to be our y equals x. A vertical shift up 2. So that's going to be a +2 tacked on the end. a vertical stretch of 4. So that's going to be 4 times our function. All right, we'll take a look at this. Y equals 4x plus 2. So it's kind of a cool equation because you probably remember in Algebra 1, oh yeah, my y-intercept is 2, my slope is 4. That means up 4 over 1. Well, this is just another way of looking at a linear equation. It's the same thing based on transformations. Up 2, because I shifted it up 2, and a vertical stretch of 4, so it pulls it in the vertical direction 4 times faster in the horizontal direction. So it's just another way to look at a linear equation or function. So the next one here is going to be a quadratic. All right, so quadratic is y equals x squared. Horizontal shift of left 1. That means inside the function, I'm going to have an x plus 1. A vertical shrink of 0.5. So that means I'm going to have 1/2 times my function, or you can put in 0.5, doesn't matter. A reflection about the horizontal axis. That means you're going to have a negative in front. Okay, so we've got y equals. Put that negative in front. That's going to be your horizontal. First thing you're going to see. Then put your value of a, your vertical stretch. In this case, it's going to be 1/2, or you can do 0.5, doesn't matter. It's left 1, so I have to have an x plus 1 in parentheses, and because it's a quadratic, this has to be squared. If you don't put that squared on there, it's linear, completely wrong based on this description. So 3, absolute value function with a reflection about the horizontal axis, a vertical shift down 2, a horizontal shift right 1, and a vertical stretch of 3. So again, absolute value, y equals absolute value of x. Reflection about the horizontal. All right, so remember, that's out in front. So I'm going to have y equals negative. There's my reflection in the horizontal. A vertical shift down 2. That means a negative 2 tacked on to the end. Horizontal shift right 1. That means inside your function, you're going to have an x minus 1. It's absolute value. Oops, a little messy. And a vertical stretch of 3 means you got to put a 3 there. Next, we have a parabola, which is the same as a quadratic. That's your y equals x squared. A vertical shift up 5, a vertical stretch of 1/2. So there's no reflections here. It's pretty straightforward. Vertical stretch is going to go out in front. Vertical shift up 5 is going to be outside the function. So this is just going to be x squared and then a plus 5. Okay, that's pretty straightforward. Just when it comes to your quadratic, make sure you understand the difference between an x squared plus 5 and an x plus 5 squared. Very different. This is a vertical shift here, but if you put it inside with parentheses, then it becomes a horizontal shift. Inverse equation. We haven't seen this since that first video. This is an inverse equation, 1 over x. Horizontal shift left 2. So horizontal means it's inside the function. So wherever the x is, that's where you have to put it. It's going to be an x plus 2. A vertical stretch of 4 and a reflection about the horizontal axis. So I've got y equals reflection about the horizontal. So I'll put the negative in first. Now if you notice, this is 1 over x. So I've got a vertical stretch of 4. That's got to go in the numerator, because if you put it in the denominator, it's actually a 1/4. So it's got to go up top. Reflection about the horizontal axis. Did that, sorry. Left 2, so that's going to be an x plus 2 down here. Okay, and a couple more real quick here. Cubic function. Y equals x cubed. Reflection about the horizontal axis. A vertical shift down 1 and a horizontal shift right 3. So a cubic reflection about the horizontal axis. That means we start out with a negative. We don't have any vertical stretch, so we don't put a number there. I've got a vertical shift down 1 and a horizontal shift right 3. So x minus 3 in the parentheses. Don't forget it's a cubic. You got to put that cube there. And the last one, radical function, which square root, reflected about the vertical axis. So we're seeing this for the first time. That means inside the function, you got to have a negative. And a shift right 2. So this one we have to be careful. So it's going to be square root. Underneath, you're going to have a negative, and you're shifting it right 2. So you've got to put that in parentheses like so. And you can just leave it like that. That's how I would prefer you to leave your answer. because this right here is your reflection in the y, or your vertical, and that is right too. Now, if you wanted to do additional work, you could distribute that negative, and you get something that looks like this. Or, this is how you might see it from time to time. But remember, when you see something like this and have to graph it, you want to rewrite it by factoring out that negative. That's something that's very important from this first day. All right, we're done. We finished day one. Probably the longest lesson in the entire year. But thanks for hanging in there, and don't hesitate to contact me if you have any questions. Thank you.